Let's talk about atomic mass. You may remember from your previous chemistry courses the discussion of isotopes. Simply put, isotopes are individual elements, individual atoms that have a unique mass number. Now, whereas the atomic number represented here on the left subscript portion of the symbol and the symbol of the element are intimately involved. And if you know the atomic number, you automatically know the name of the element or the element symbol, and vice versa. The mass number can change from one isotope to another. And simply put, the mass number is the combination of the number of protons and the number of neutrons present in the nucleus of that element. Now, what ultimately changes the mass of one isotope to another is the fact that the number of neutrons can change. The number of protons has to remain the same so that you still have the same element, but having different neutrons gives you different mass and different isotopes altogether. If you look up the different isotopes that have been known, that have been discovered, and some of them which have been man-made, you realize that throughout the periodic table there's actually a wide array of isotopes present. So this is a small list ranging from radium up until neptunium. And you can see that in the periodic table, whereas we represent all the elements in a column, in this nuclei chart that was published by Lockheed Martin, each one of the elements is actually present in an entire row, and in that row you see the atomic mass increasing, going from left to right, and there's a lot of them. And this table actually gives you a lot of information that we're not going to discuss in this class. It's a little bit beyond our purposes, but the main point is that there's a lot of isotopes. Now, what we're going to really focus on in terms of isotopes is the natural abundance of the element. And that basically means that we are only really interested in the isotopes of each element that are naturally found, not the ones that are man-made. So if you look at the P block of the elements, so this highlighted orange region, from boron down to iodine, and I'll include even hydrogen in this list. What you can see is that if you actually zoom into these individual elements, you will find out that they actually have, some of them, a fair number of isotopes. A few others have a lot of isotopes. So for instance, notice that aluminum, phosphorus, arsenic, iodine, they only have one natural isotope. And that isotope automatically dictates the mass of that entire element. But then you have other elements like even hydrogen, right? One of the isotopes is very small in quantity, so mostly proto-hydrogen is the one that determines the mass of hydrogen. But there's other elements where you have two isotopes like boron or carbon, nitrogen. I'll even group oxygen with them because oxygen 17 is very low in abundance. But there's other elements where you have as many as 10 different isotopes that naturally occur in the element. So basically what happens is that because each isotope has a different mass, but they all represent the same element, when you grab a batch of sample of any element, you're really grabbing a batch that contains all these different samples of that same element. And so their average masses is what ultimately gives you the atomic mass of the element. And mathematically, we represent that with this formula. Simply stated, we multiply the mass of the isotope by its ratio. And the ratio is simply the abundance percentage of that isotope divided by 100%. All right, so I'm going to give you an example. So boron, I mentioned, it has two stable isotopes, boron 10, 20%, and boron 11, 80%. Now, to find the atomic mass of boron, we need to know the isotopic masses of boron 10 and boron 11. And those are values that I have to give you so that you can find the atomic mass. But you could be given the atomic mass and most of the values, except for, let's say, one of the isotopic masses, and be able to find that mass. So in other words, you'll have 4 knowns and one unknown in this list. So here we're just going to go for the atomic mass of boron, which implies that we will have to have the isotopic masses given. So these isotopic masses will be values that I'll have to give you. And notice right here that the 0.20 and the 0.8, that's technically the percentages of boron 10 and boron 11 divided by 100. So once you divide that percentage by 100 and multiply it by the atomic mass individually, you can then add those values together, and this gives you the atomic mass of boron, which is what you see in the periodic table. Another example, carbon. Carbon 12 and carbon 13, those are the main constituents of carbon. You do the same thing. Carbon 12 is multiplied by 98.9 divided by 100% plus the isotopic mass of carbon 13 times 1.1% divided by 100%. And you multiply the corresponding values with each other. Notice, by the way, that the isotopic mass of carbon is exactly 12.00000, etc. That's not a coincidence. That's artificially made that way. In fact, if you want to think of it this way, the entire periodic table is based in terms of mass from the idea that carbon is calibrated to be exactly 12.000. So that's kind of our base mass number for everything else. That being said, you still carry on with the same logic right here. You multiply the isotopic mass by the ratio. You do that for every single isotope present in the element, and then you add them together to get the mass. And one thing that you'll notice is that for the isotope that has the higher percentage, the atomic mass tends to be closer to that mass number than for the other isotopes, right? So boron 11 is present in the greater amount, so we have an atomic mass close to 11. For carbon, carbon 12 is the one that's present in the greatest amount, so we have an atomic mass close to 12. For nitrogen, we have two isotopes, nitrogen 14 and 15, and based on the percentages, you should expect the atomic mass of nitrogen to be close to 14 at the end. And that's exactly what happens. You plug in the isotopic masses of nitrogen 14 and nitrogen 15, multiplied by the ratios, added together, and you end up with these values. If you ever end up with an atomic mass that is, in the hundreds or thousands, that should be a cautious sign to you that you've made a mistake. The atomic masses should be close to the isotopic masses of the isotopes themselves, and they shouldn't be jumping by factors of 10 or 100. And if that ever happens, what that means is that you forgot to divide the percentage abundance by 100%. So be on the lookout for that. All right, we'll do one more, oxygen. And we'll take these three isotopes. Now, oxygen having three isotopes means that we're going to have to carry out the operation of multiplication 3 times. Once for oxygen 16, once for oxygen 17, once for oxygen 18. And each one of the ratios, the abundance percentages, will be divided by 100, right? So these numbers right here should be values less than 1. Plugging in the actual isotopic masses of oxygen 16, 17, and 18, carrying out the multiplications and adding the numbers together yields the atomic mass of oxygen. And once again, oxygen 16 was the one in greatest abundance compared to the rest of the isotopes, so it's not surprising that the atomic mass of oxygen lies very close to 16. All right. Now, elements that I think you should definitely remember. I don't want you to memorize the masses, but you should, keep in mind, because we're going to use a lot, are hydrogen, carbon, nitrogen, oxygen, the halogens, and possibly from time to time phosphorus and sulfur. So it might not be a bad idea to kind of get familiar with these atomic masses, but I don't necessarily need you to memorize them. But you might actually come to just remember them because we're going to use them quite a bit. Now, for these elements, the isotopic distribution is rather interesting. Now, fluorine, it's only present with one isotope, so the mass of fluorine 19 is the mass of fluorine. Same thing for phosphorus, right? But chlorine has multiple, it has two isotopes, and it's in a ratio of 3 to 1. Bromine has two natural isotopes, and it's in a ratio of 1 to 1, roughly speaking. And these elements we're going to see play a role, in the chemistry that we study in this class. You'll also actually encounter that particular feature in organic chemistry in the future. All right, now let's talk a little bit about the spectrometry that allows us to measure the masses to such level of accuracy for these isotopes via a technique known as mass spectrometry. Now, mass spectrometry uses very sophisticated instrumentation, some of it even more impressive looking than others. But the machines shown up here are basically used to determine the masses of the elements or molecules you may have. And it does it by a very simple approach. Namely speaking, it removes electrons or adds electrons depending on the instrument you're using. But we'll stick with the conventional feature, which is to remove electrons. So the idea is that if you add enough energy to an atom, enough for it to basically remove one of its electrons, what's left behind is a charged particle known as a cation. And this cation has a mass which hasn't been altered all that much because the mass of the electron is very small compared to the masses of the rest of the atom. But that mass to charge ratio is ultimately what we use to determine the masses of the elements themselves. And the way it works is as follows. You inject a sample of your molecule or element into the mass spectrometer. And in this inlet, the first compartment is held at lower pressure, lower than 1 atmosphere. So what ends up happening is that once you inject your sample, you kind of create this dispersion where the entire liquid sample that you have, or gas sample, depending on what you're handling, kind of disperses around the compartment. But then there is this other inlet that leads you to a compartment that's held at even lower pressure. So you have kind of this pooling effect into the next compartment. But what happens in this compartment is that you are received or collided upon by incoming electrons using something known as an electron gun, which is literally shooting electrons in the perpendicular plane of where these atoms are flying. And when this happens, the collision provides enough energy to remove electrons from the atoms or molecules that you have in here. And it's kind of an interesting thing because you are using electrons to remove electrons from a different, substance. So you end up generating a lot of electrons here. So what that means is that you have to kind of segregate these things from each other. And the way you do it is by now introducing voltaic plates of negative potential. So you place these plates of negative potential at this end, which then attract the positive particles that you've just created. Some of them make it through this inlet and they get basically delivered to what we call a discriminator, a mass to charge discriminator. In this case, the one I'm showing is known as a quadrupole, but you could use magnetic fields, you could even use length to determine the mass of the particles. And once the charged particle goes through the discriminator, it reaches a detector, at which point it gets amplified in signal to millions, maybe even billions of electrical signals for every one collision that happens on the detector. So what this means is that you can have very small quantities, like very, very small quantities of a substance and be able to detect its mass to a high level of accuracy. And this is the power of mass specs. All right, so now the last thing I'll show you is a periodic trend of atomic mass, which is kind of cool to see now that you have the periodic table and the atomic mass is kind of explained in terms of their isotopes. And generally speaking, what you see in terms of atomic masses is that when you look from left to right, the atomic masses increase. And this generally makes sense because you are increasing the number of protons going from one element to another, and each proton carries mass, so the mass has to go up. So that makes sense. And from top to bottom on the periodic table, the same idea follows. As you go from top to bottom, you have a lot more electrons and a lot more protons and neutrons, so the mass goes up. So generally speaking, from left to right and from top to bottom, the atomic mass increases. But then, if you look carefully, you'll realize that there are some pockets where this isn't exactly true. For instance, between cobalt and nickel, the atomic mass actually goes down. Not by a lot, but it does go down. And from tellurium to iodine, same idea. the mass goes down. And you see the same type of business happening all the way down here in the bottom of the periodic table. From thorium to protactinium, the mass goes down. From uranium to neptunium, the mass goes down. From plutonium to americium, the mass goes down. And from from curium to berkelium, the mass goes down. So what's happening? Well, what's happening is that not all elements have the same number of isotopes. As you saw in this previous table, some of the elements have a few isotopes, and a few other elements have a lot more isotopes. So in the case of tellurium and iodine, you can see that, well, iodine only has one stable isotope, iodine 127, but tellurium has a total of 8 different isotopes, and it so happens that tellurium 128 and tellurium 130 are actually present on a fair percent abundance. And so that allows tellurium to end up having a higher mass than iodine as an element. But if you do compare tellurium 127 to iodine 127, you'll find out that, yeah, the trend actually kind of follows what you would expect. But for the element being an average mass of all the isotopes, that isn't exactly true. So it's actually rather surprising that for the vast majority of the elements, you do see a very smooth trend from left to right and from top to bottom in the periodic table. Okay, so with all of this, I'll leave you here and I'll meet you in the next video.